A modern container ship can weigh over 200,000 tons. That's heavier than most skyscrapers. When strong wind hits its side and ocean currents push against it, the force is massive. We're talking about pressure strong enough to snap thick steel cables. And yet, that entire floating city can be held in place by what looks like a single curved piece of metal dropped into the sea. But here's the surprising part. If you drop that same anchor in the middle of the deep ocean, it wouldn't work at all. And if you tried to pull it up the wrong way, you could seriously damage your own ship. So how does it actually work? How does a 20-ton anchor hold something that weighs 200,000 tons? How do sailors know how much chain to use? And what happens when the ocean is simply too deep? Today on Ordinary Things Deep History, we're breaking down the heavy engineering behind one of the oldest tools in maritime history, the anchor. First, forget what you think an anchor does. It doesn't just grab the seabed like a claw. The real power of an anchor system is not just the anchor, it's the chain. On large ships, the anchor chain is enormous. A single link can weigh over 300 pounds, heavier than most home refrigerators. The full length of chain attached to the anchor can weigh more than the anchor itself. That weight is not a problem, it's the secret. When a ship drops anchor, the crew doesn't just lower it straight down and stop. They slowly release a long length of heavy chain onto the seabed. Instead of forming a straight line, the chain curves naturally along the bottom. This curve is called a catenary. You don't need to remember the word, just imagine a heavy rope sagging between 2 points. That sag is extremely important. Here's why. When waves push the ship backward, the ship pulls on the chain. But before the force reaches the anchor, it must first lift all that heavy chain lying on the seabed. That takes energy. By the time the force finally reaches the anchor, it's pulling almost sideways, not upward. And anchors are designed to resist sideways pulling. When pulled horizontally, the anchor digs deeper into sand or mud. It buries itself and becomes harder to move. The more steady pressure you apply, the more it holds. So it's not just a hook. It's a system of weight, angle, and friction working together. Now let's talk about deep water. Imagine a ship breaks down in the middle of the Pacific Ocean. The water below might be 2 miles deep. Can the ship just drop anchor? No. Most commercial ships can only anchor in water up to about 100 meters deep, around 300 feet. Why? Because the chain itself becomes too heavy. If you tried to lower enough chain to reach miles down, the vertical weight of that hanging steel would be enormous. It could overload the windlass, the powerful motor that controls the chain. In extreme cases, it could even damage the front of the ship. So in deep ocean water, ships don't anchor, they drift. Or, if they are modern drilling or research ships, they use something called dynamic positioning. Computers control powerful thrusters around the ship, constantly pushing against wind and current to keep the vessel in one spot, without ever touching the seabed. It's like the ship is swimming in place. Now here's another question. How does the captain know how much chain is in the water? They can't see underwater. They can't guess. The answer is surprisingly old-fashioned. Anchor chain is measured in sections called shackles, sometimes called shots. One shackle is about 27.5 meters long, roughly 90 feet. Each section is connected by a special link. These connecting links are painted bright colors. Some crews even wrap wire around certain links so they can feel them at night. As the chain rushes out through the pipe at the front of the ship, a crew member counts the colored markers. 3 shackles in the water! That message is radioed to the bridge. This tells the captain exactly how much chain has been released. The amount of chain compared to the water depth is called scope. More scope usually means better holding power because the pulling angle stays low and horizontal. Too little chain? The anchor might drag. Too much chain? The ship may swing too widely. So anchoring is not random. It's careful measurement and calculation. Now comes the hardest part, getting the anchor back. Remember, the anchor may weigh 20 tons, but when it's buried in mud, it's not just heavy, it's stuck. Mud creates suction. Think of pulling your shoe out of thick, wet ground. That resistance is suction. You cannot simply pull straight back with the winch. The motor would struggle against both weight and suction. Instead, the ship moves slowly forward, directly above the anchor's position. As it does, the chain becomes vertical. This changes everything. Instead of dragging the anchor sideways, the ship now pulls straight up. That vertical pull breaks the suction seal between anchor and seabed. Sailors call this moment breaking out. Once freed, the anchor rises covered in thick mud. Before it comes fully on board, high-pressure seawater jets wash it clean so the inside of the ship doesn't fill with sludge. Then it's locked tightly against the hull, and the ship is free to move again. Anchoring looks simple from the outside. You see a ship, you see calm water. You assume it's just sitting there. But below the surface is a carefully engineered system of steel, weight, angles, and physics. From massive chain links weighing hundreds of pounds to color-coded measurement systems used for centuries, anchoring is a mix of brute force and precise calculation. It's not just a metal hook. It's gravity, geometry, and engineering working together under the sea. If you enjoy learning how ordinary things hide extraordinary history and design, subscribe to Ordinary Things Deep History. Because sometimes, the most powerful technology in the world is the one you never notice. Thanks for watching. I'll see you in the next one.